We'll go ahead and get started. Welcome back. As you recall, last time we were talking about carbocation rearrangement, and I think I already walked you through what happens with cholesterol as a demonstration for carbocation rearrangement. In terms of whether each proton sort of leans over and makes a new bond, and then we get another intermediate, and then we do the next step, or whether it happens all in the same step is kind of murky. If you were to draw an energy landscape for this carbocation rearrangement, it would be kind of broad and smooth with maybe the smallest sort of intermediates, and so it's not clear whether you should draw the mechanism in individual rearrangement steps or whether you should just do this kind of thing and call it good. But we walked through a carbocation rearrangement last time, so just envision each of these individual arrows as meaning that this hydrogen with its electrons leans over. You get the bridged carbonium type intermediate, and then it leans over more to form a full new CH bond here and would leave a positive charge there. And then we're going to do that again and again with this methyl group and again with the green methyl group. And in so doing, we end up with a positive charge on the tertiary carbon. I guess the other thing I want to point out is that at each stage along this rearrangement pathway, you end up trading one tertiary carbocation for another. And so you'd expect the energy changes to be small. In general, the trading from one tertiary carbocation to another directs where the positive charge goes. For example, with carbon 18, we're not going to move over a CH bond from carbon 17 because that would give us a less stable secondary carbocation. Instead, we move the one on 14. Similarly, once we have the positive charge on 14, we move this methyl group so we can have it on 15. So it's this process of going from one tertiary carbocation to another. Go ahead.
Just kind of, I understand like how hydrogens would move, but it kind of surprised me that those methyl groups would be able to move.
Yeah, the methyl group can do rearrangement in that way too. It's larger than the hydrogen, but it's also, I think maybe last time, let me make sure, we were talking about carbocation rearrangement. Yeah, a methyl group can sort of lean over too, right? So it involves the same thing, only it's bigger than a hydrogen. You get an intermediate where 2 electrons are shared among 3 atoms, and then it leans over completely to make the new bond. Nope. There we go. So some folks in the first hour asked, well, why does the positive charge stop here? Why don't we continue doing rearrangements that would continue to trade one tertiary carbocation for another? The answer is, I don't know. Some people sort of hand wave and say, well, the enzyme makes it be that way. There's some, I think, computational evidence that this is the lower energy option of the available other options. And so it's possible that's just where you sort of stay until a base comes along and removes a beta proton in an E1 style elimination. You'll notice there are other beta protons present as well, these two here, and those don't get eliminated, and in terms of why, it probably has to do with alkene stability. Notice that in the product we have a tetrasubstituted alkene, whereas if we had done the elimination from here, it would only have been trisubstituted. So this is a really beautiful example of a process occurring for reasons we can understand, right? We know why tertiary carbocations are stable. We know why tetrasubstituted double bonds are more stable than trisubstituted double bonds. And so, based on these physical principles, the growing up of this structure makes a lot of sense. Already with this 3 6-membered rings and 1 5-membered ring, you're building up the core of all sorts of steroid hormones and other molecules in biology. It takes another 19 more steps where you lose these 3 methyl groups, you reduce this double bond, and you move this double bond over here. But once you do that, you have the molecule cholesterol. And if you look at that, people sometimes give letters to these 6 or to these 4 rings, A, B, C, and D. Other people whimsically call it 3 bedrooms and a bath. I think that's personally a stretch, but you can go ahead and try it in biochem and see whether it gets a response. Yeah, I kind of shrug my shoulders and roll my eyes at that one. And I like nerdy OChem jokes, so that's gone a bit too far. Anyway, if you look at the cholesterol structure, you notice that it's got a polar hydroxyl group here. The rest of the molecule is fairly nonpolar, especially this hydrocarbon tail. And this is what makes cholesterol membrane soluble. This is why cholesterol in your blood isn't actually floating around as the own molecule in its blood, but it's carried by a high or low density lipoprotein particle. And cholesterol indeed embeds itself in cell lipid bilayer membranes and affects their physical properties. But it is also the precursor to a bunch of other molecules, which I'm just going to show you because I think they're cool, and you'll encounter them in biology and biochemistry and in future classes that you have. And just want to point out a few things. The steroid hormones are all derivatives of cholesterol. And most of them involve truncation of this nonpolar chain and then modification and installation of polar functional groups on the ring. So shown here is estradiol. You've taken that nonpolar chain off completely and installed an OH group there. Everything else is the same, other than you've lost a methyl group and you made the first A ring aromatic. You made it a benzene ring. Testosterone instead has the same C and D rings as estradiol, but it has a ketone and a cyclohexene instead of a benzene ring here. It's interesting to me that the structures can be similar on one part, different on the other, and that has dramatically different effects for development. Progesterone is interesting. It sort of mimics testosterone on the other side. It has the same A and B and C rings, but its D ring is different, both from testosterone and estradiol. It's got a ketone here instead of the OH group. This is a theme throughout all of chemistry and biology. Structure leads to function. And small structural variations in organic molecules can have dramatic consequences. Estradiol, progesterone, and testosterone each bind receptors differently and therefore each have different biological effects. Cortisol is, I guess, most closely related to testosterone and progesterone, only we've got a new OH group here and the truncated tail is different. It's a ketone with an OH group. This is a stress hormone. It's called a glucocorticoid. You'll learn in biochemistry what processes it controls. But if you make a few modifications to it, you change it from a glucocorticoid to an anti-inflammatory molecule. So prednisone involves installing a double bond here and oxidizing that OH to the ketone. And then cortisone is just the version of cortisol where the ketone has replaced that OH group. And some of you have likely had the experience of injuring an arm or a joint somewhere and getting a cortisone injection to decrease inflammation. And that's what they shot in your arm, which is kind of fun to know what's being injected into you. Vitamin D, if you've ever heard someone say, well, you need to go get some sunlight to get some vitamin D. Vitamin D comes from cholesterol. That's why it's a fat-soluble vitamin. It's lipophilic, just like cholesterol is, hydrophobic. This is a derivative of cholesterol where I think we've got one more double bond than cholesterol has. Yeah, we put another one here. And holy Texas carbon. Why did I do that? That was a shameful experience. Okay. In any case, in a reaction we won't talk about in this class, and you may have to wait till 352 to get this particular six-membered ring under UV light can open up. And it gives you this molecule called cholecalciferol or vitamin D3. And so getting UV light is a trade-off between vitamin D and sunburn, and humans across the world have developed different ways of, or rather evolution has developed different ways of dealing with that trade-off. Folks that come from, or I mean, come from, I mean over the past 200,000 years from more equatorial climates where you get direct sunlight, get plenty of vitamin D. The key thing to avoid there is skin cancer, and so they express more melanin in their skin. Folks that are from higher northern or more southern latitudes tend to not get quite enough UV light, and so they don't produce as much melanin so that they can have more vitamin D, and it's sort of a trade-off. Why, just as an aside, why anyone anywhere thinks this chemical process should have anything to do with how we treat other individuals is beyond me, and that's something we all need to work on. And soapbox, I promise not to record too many more speeches that I email to you because I don't want it to sound like I'm running for office or something like that. I'm Josh Price, and I approve this message. Yes? No. Yeah. The only thing I want to be president of is some Star Wars fan club. I think that's probably all I would want to be.
President Price has a cool ring to it.
Yeah, you know, I served as Elders Corps president 4 or 5 years ago, and it was one of the darkest times of my life. It was, you will hear people talk about how they really enjoyed service and they just enjoyed interacting with and serving people. And I did too. I always felt better once I got out and talked to people, but that was hard. And the other part I struggled with was the endless supply of meetings where we talked about how we weren't doing enough of the things we were supposed to be doing. That was kind of hard on my mental health, but then I got released, and it's been great. Oh boy, I'm going to tell you a story now because we've got a couple minutes. The one calling I aspire to in the church is primary chorister, and that is the one calling I will never get, at least in our current ward, and I will tell you why. I've been primary pianist a lot. Primary chorister is so much fun. I got to substitute once, and I made the mistake of telling the kids, and I think it was the senior primary, I made the mistake of telling them that it was sort of funny on the Jonah verse of Follow the Prophet to sing Swallow the Prophet, which the kids thought was hilarious, but the actual primary chorister, when she returned, was not amused. And she's now married to our current bishop, so I think that option is just forever foreclosed. I'll keep you posted. But I am in the primary now, such as it is, which is non-existent, and we're looking forward to getting back. The pure gospel of Jesus Christ is taught in the primary, I can tell you that. You don't tell primary kids that we need to be working more to do this or that. We just talk about loving one another and following Jesus, and that's good stuff. All right. What else do I need to say that's embarrassing to myself or others? I think we'll stop there. Bile salts. This is what makes it so you can handle fat in your diet. This molecule is called taurocholate, and depending on what this side chain group is, it can be different. It may not appear to you why. So the property of this molecule is it solubilizes fat. It's an emulsifier or a surfactant. It's kind of like soap. May not be apparent to you how that's the case until you imagine the A, B, C, and D rings as sort of a plate, it's the structure of that is a little more complicated. It's more curved, kind of like a claw. So you can think of the ring as sort of, the ring structure sort of curving down away from you. On the top of the ring, you've got nonpolar groups, methyl groups, hydrocarbon stuff, CH bonds. But on the bottom, towards the bottom face, you've got polar functional groups. So you've got a nonpolar side and a polar side. These are great for encapsulating fat droplets and making them soluble in the GI tract. This is why if you don't have a gallbladder, you have to be somewhat careful with how much fat in your diet. And if these bile salts crystallize out too much, you can get lovely gallstones, which are painful to deal with, but look kind of cool. I don't think, though, that there is an industry in gallstone jewelry, or at least if there is, there shouldn't be. That sounds kind of gross. Okay. What a day. All right, well. So one more reaction I want to introduce is a reaction to avoid carbocation rearrangement in alcohol dehydrations. And this is the reagent POCl3 that I think I mentioned last time, or POCl. It works very much like SOCl2 and PBr3. I didn't mean to indicate with the numbers that they were different steps. You add POCl3 and pyridine as a base. I won't show you the mechanism for this reaction because the text describes it in sufficient detail and I don't really have anything to add. The process turns OH into a good leaving group, but before it can leave, pyridine as a base does the E2 reaction, so there is no carbocationic intermediate. And therefore, the only elimination product you get there is that one. So, how might I ask about this in an exam context? Well, I might show you a situation. I might ask you for, I want to get this product from this starting material. What reagent should I use? And if you're not paying attention and you don't look for the possibility of carbocation rearrangement, you won't select the right reagent. All right, questions so far? Yeah.
Could you repeat that really quick, that last thought?
Yeah, I might give you this product and this starting material and ask you what reagent gives you only this product. If you don't pay attention to the possibility of carbocation rearrangement, you might propose different conditions than the ones that actually work. All right. So the last thing we need to do in Chapter 9 that we may not have quite enough time to finish up with is to talk about epoxides. Epoxides are the exceptions to the rule that you got to first turn OH or OR minus into a good leaving group. Recall that a while ago I told you that doing an SN2 reaction on an ether where OR minus was the leaving group was a terrible idea because OR minus is a terrible, horrible, no good, very bad leaving group. The exception to that, though, is when your ether is part of a strained three-membered ring. So I want you to imagine that the two carbon-oxygen bonds are pointing out of the page towards you, some CH bonds going back into the page and some in the plane of the page. A nucleophile can attack from behind in an SN2 fashion, and I mean a good, strong nucleophile, to cause the negatively charged oxygen to leave. As with any SN2 reaction, it happens via backside attack on the corresponding sigma star antibonding orbital. And you get inversion of configuration if you're attacking at a stereocenter. I've tried to represent that here, though the carbon this nucleophile attacks is not a stereocenter. When you open up an epoxide, notice that the OR minus leaving group is still part of the same molecule because carbons 1 and 2 are directly connected to each other. But the reason this is okay is because of the relief of ring strain that happens when that OH minus leaves. So the relief of ring strain pays for the fact that OR minus is a cruddy leaving group and makes these reactions work really, really well. Usually when we do this reaction, either the solvent has protons that can be used to protonate the negatively charged oxygen, or after the reaction we do some kind of workup where we add water buffered at some pH, and whatever needs to get protonated gets protonated. And so the product of opening up an epoxide is going to be, I guess I want the numbers to be a little different. The product of opening up an epoxide is going to be an alcohol on carbon 1 with a nucleophile attached to carbon 2. So you're going to have this sort of 1-2 substitution pattern. All right, questions so far about epoxides? Go ahead.
You might have already said this, but could the nucleophile attack from both 1 and 2 carbon, like could it attack either side, and also would it change if they weren't the exact same, like if there's different substitutions?
Great question. So can the nucleophile attack carbon 1 versus 2? Totally. Here they happen to be identical. Witness here the plane of symmetry, so you'll get the same product from either one. We will deal in just a few minutes with a situation where the two carbons are not the same, and we'll have to make a decision.
Okay.
Yeah.
So the goal here is, I know like what we've been doing in the past is just converting the alcohols to either the groups and we do those other reactions. Is that the goal here? So then we could go ahead and replace or make that OH group with the to do the rest of the reactions? Is that?
So if you wanted to, yeah, the question is our goal to turn OH into a good leaving group to do more reactions? Well, with this alcohol, you could go on to do other things that we've learned to do with alcohols. I guess the point is, if your starting material is this epoxide, which is this weird example of an ether in a 3-membered ring, you don't have to turn the oxygen into a good leaving group first because you're relieving ring strain. Yeah. All right. Anything else? Yeah.
Under what circumstances do 3-membered rings like that happen?
When do 3-membered rings like that happen? Actually, all the time. We haven't learned how to make epoxides yet, but in chapter 10 and again in 12, we'll have a way of doing it. And it's actually really easy. You just need an oxidizing agent. So I may punt until then, but they're pretty straightforward to make. Good. Others? Okay, so because of the SN2 nature of this reaction, epoxides are a really good playground for testing your understanding of stereochemistry and molecular structure. So if you're struggling with spatial reasoning and shapes of molecules, you're going to want to work on that before we get too far in. So first of all, when you draw an epoxide, there's a number of ways to do it. You can draw it with the carbons in the 3-membered ring all in the plane of the page, and then substituents are wedges and or dashes. Alternatively, you could draw the molecule, you could sort of grab the oxygen of the epoxide and bring it forward out of the page. Oh, what the heck? Bring it forward out of the page, and that would tip the methyl groups back into the page and bring the protons here. I've even seen people drop the wedges for the hydrogens and just imagine looking straight down on the epoxide with the oxygens here. All of those are viable options. There's no one right way to draw an epoxide, but you've got to choose a way that helps you understand the stereochemical consequences of the reaction. Man, I want to shrink that a little bit. It doesn't. There we go. No. Oh well. Okay. So let's talk about stereochemical consequences of the reaction. The starting material, epoxide, and we'll call these atoms, I don't know, A and B. If you look at this epoxide, there's a plane of symmetry right through the middle. This epoxide is not chiral, and it is also a meso compound because it has stereocenters. Carbons A and B are equivalent, so it doesn't matter which one we attack. We can attack one or the other, and either will give us the products that we are getting. So imagine a nucleophile coming in and attacking, and let's let our nucleophile be OH minus, and usually this is in water. Good nucleophiles can open up epoxides directly. They can attack without any other precursor. And so we can imagine from either of these drawings the OH approaching carbon A or carbon B from directly behind the carbon-oxygen bond, and the leaving group leaves. So I'm going to attempt to draw the same reaction from all of these different perspectives, and hopefully when we do that you'll be able to reason your way through it. Oxygen, OH coming in from behind, leaving group leaves. Same thing here, OH coming in from behind and leaving group leaves. So let's draw the products that come, the product that comes from that. If we're drawing it from sort of viewpoint 1, we would draw the negatively charged oxygen here and the nucleophile here. We'd show the methyl group on carbon B still where it was, unchanged. On carbon A, we need to show the methyl group still pointing out toward us, but now oriented toward the top of the page. Proton pointing down away from us, but oriented toward the top of the page. So that's one option. And alternatively, from view 2, we could keep the two methyl groups like this. We would have the negatively charged oxygen here, proton would be up, and nucleophile would be down. And I think if we reasoned through it, we would get the same answer from view 3. The key point is inversion of stereochemical configuration. All right? That may take some practice. I will point out that after the negatively charged oxygen leaves, it picks up a proton from some source, probably the solvent, water, and then your final product is shown here. And the stereochemical nature of this product, oh, we said the nucleophile was OH. I'm sorry for not committing by writing that OH down there. Now, I could ask you at this standpoint, at this point, is our molecule, our product, chiral or not? This is now an exam 2 question. So is it chiral or not? Well, the starting material was not chiral. Let's look at the product. And as always, it's easier to see whether something's chiral or not if you draw the similar groups eclipsed with each other. So I'm going to rotate around this carbon-carbon bond such that the two OH groups are eclipsed with each other. Doing so would take the methyl group, which used to be pointing up toward us, toward the top of the page and out at us, now be oriented toward the bottom of the page and back into the page away from us. So with that view in place, what do you think? Chiral or not? Yes, to which? Yes, it is not chiral. Yes, it is chiral. Yes, this molecule is chiral. It is not the same as its mirror image. Now, I told you before that there is no way, world without end, that you can take a non-chiral starting material and get one enantiomer out as the product. So, what am I missing here? Okay, well, the other enantiomer, fine. Where would that other enantiomer come from? I mean, we could draw it. That wouldn't be hard, but I do want you to see where we get that enantiomer from. It might be easier to see if we draw it like this. Where do you think we got that other enantiomer from? Go ahead.
Is that if nucleophile attack B instead of A?
Exactly. Yeah, we get the other enantiomer from attack at B instead of attack at A. Yep. So you take the meso starting material and you open it up with OH minus and you get a 1-to-1 mixture of enantiomers as your product. So you got to be able to follow through the stereochemistry of your epoxide starting material down to the correct stereochemistry of your products. Another thing to point out is just a structural pattern, and it will get more and more important to see this as we go on. The product of opening an epoxide with OH minus is a 1,2 diol. So anytime you see OH groups on adjacent carbons, you can think, hey, I might have gotten that by opening up an epoxide. All right. So the epoxide opening is an example of a reaction that is what we call stereospecific. This means that stereochemical information in the starting material determines the stereochemical outcome in the products. Notice that we don't get any of the other possible diastereomer from this meso epoxide. You just can't. If we wanted to get that other stereoisomer, we could start from, and I'm not sure what we could start from the alternative chiral epoxide. There's no plane of symmetry here. There is another element of symmetry, and that is an axial symmetry. If we draw a line through the oxygen and through the carbon-carbon bond between A and B, and we rotate 180 degrees around that line, we get the same thing. This molecule is what we call C2 symmetric. That's a term you can promptly forget, but I might use again. And A equals B. So we can assume that as above, a nucleophile will attack A at the exact same frequency as it attacks B, and that we'll get the same product from attack of A or B. So let's have OH minus open up this epoxide. Oops, let's use red for the arrow. Attack from behind. I'm not going to draw the negatively charged oxygen intermediate. I'm going to show what it looks like once it gets protonated. Here is the new OH group that came in. The methyl group is still oriented out toward us, but now pointed towards the top of the page. Again, in order to see whether this product is chiral or not, it can be useful to redraw the molecule in such a way that the similar groups are eclipsed. And if you do that, it becomes clear that this epoxide is not chiral. It is a meso compound. Interestingly, if you open up the chiral epoxide with an OH group, you get a meso diol. which would be a terrible thing to do. Why the heck would you want to do that, right? Why would you want to take a non-chiral or a chiral starting material and end up with a non-chiral product? You probably wouldn't, but the point is that these two epoxide starting materials, I have to stand sideways to be able to do that, were diastereomers, and the products are also diastereomers. And this is another demonstration of the principle of a stereospecific reaction. In a stereospecific reaction, if you use a diastereomer as the starting material, you're going to get, well, stereochemical information is transmitted from starting material to product. So the products from one stereoisomer are going to be different and have to be different from the products from another stereoisomer. All right, questions so far about stereochemistry? That's really important because it tests so many things at once. And so it's easy for me to, for example, draw a diol product like this, I guess, plus it's an enantiomer, and say, okay, friends, what was the starting material? So that ought to be pretty clear based on our discussion above, but go ahead and work on that and see if you can figure it out. Take just a minute and see what you can come up with. pH, by the way, stands for a phenyl group, which is a benzene ring as a substituent on something. Last, I think in winter semester of 2020, when I would do in-class questions like this, I would play the Jeopardy theme song. And actually people got angry. It said it stressed them out as they were working and the song got closer and closer to the finish line. So we stopped doing that. All right, so you want an epoxide starting material. Any idea what the stereochemistry needs to be? Say that louder, sorry. You want the achiral starting material, so where would I put my benzene rings? Front or the back, either way it's the same. Okay, good. And if that was a bit of a struggle for you, the first thing you want to do is say, okay, how do I know how to make this 1,2 diol? You know how to do it via epoxide opening, and you know epoxide opening is trans, or happens from the backside. So draw the two OH groups anti to each other, and then get the rest of the molecule oriented in the right way. And then just think backwards. Imagine that this OH group backs out. We lose the proton there, and we make a new carbon-carbon bond here, and that's going to keep the phenyl group on that backside but push it downward, and that's the precursor. All right, so this is an example of retrosynthesis, or using the information in the products to predict which stereoisomer epoxide you would have to use. It's going to get worse than that, though, because after chapter 11 or 12, I'm sorry, after chapter 10, I will be able to ask you, there's a specific reagent that you can make the epoxide from the alkene. And so I'll be able to go back even another step and say, which alkene stereochemistry would you have had to use? But we won't worry about that now. Okay. So far, in our examples, all of them have carbon A and carbon B have both been the same. So we haven't had to worry about which one gets the incoming nucleophile. However, there are a lot of examples you could think of where the two carbons would not be the same. And we want to think about what the outcome should be in that case. So here's an epoxide, here's A, here's B. Let's use a strong nucleophile. I'm not sure what we want to use. Let's just say CN minus or any other strong nucleophile. So the mechanism is going to be SN2 backside attack with inversion of stereochemical configuration. Based on what you know about SN2, is there a difference between carbons A and B? Which do you predict will be faster or better? B should react better with CN minus. Why? Sterics is the key issue for reactions like this. I don't know what the air quotes are. I told you about my Aunt Dinah and air quotes, didn't I? Yeah, all right. I don't know what stories I've told. Anyway, sterics, yes, the less substituted carbon will be preferred by this strong nucleophile. So CN minus will come in from the backside and attack at less substituted carbon B. And after we protonate the negatively charged oxygen, we will end up with that structure. So this is an example of a reaction that is regioselective. It is selective for forming a new carbon-carbon bond with B and not with A. The other alternative would be a regio or constitutional isomer. If we attacked carbon A instead, we'd have different connectivity, and so it would be a different constitutional or regio isomer. Okay, so when you're using a strong nucleophile and when your leaving group is a negatively charged oxygen, sterics matter most. Now, you can also open up epoxides under acidic conditions. So let's take the same starting material. And now let's use HBr. What happens here is that we first protonate the oxygen of the epoxide. Lone pair electrons on the oxygen attack the proton of HBr, just simple acid-base chemistry. And then Br minus can act as the nucleophile. Now, the interesting thing is that what we observe under these conditions is Br minus actually attacks the more substituted carbon A instead of less substituted carbon B. Opposite regioselectivity. In this case, the nucleophile reacts in such a way that you form the bond with the more substituted carbon. Okay. So let's try to rationalize our way around that. Would you still get the other product just in smaller amounts? That is a great question. The answer is that sounds reasonable to me, though we're going to assume that the reaction is perfectly regioselective. It might not in reality be. All right, let's try to talk about why we get this opposite regioselectivity. What do you remember about the SN1 reaction? Is it faster for tertiary or secondary leaving groups? Faster for tertiary, and that is because because the tertiary leaving group leaves behind a more stable tertiary carbocation. So, sorry. The fact that we observe the nucleophile attacking the more substituted carbon could be consistent with the leaving group ROH leaving from the more substituted carbon to leave a positive charge there instead of the other option, because that's the more stable carbocation. So if the mechanism were SN1, that would explain the regioselectivity. What we would be saying is, and this is just a hypothesis at this point, we got to make sure it's consistent with our data. What we would be saying here is that maybe the protonated oxygen is a good enough leaving group to leave on its own, and instead of leaving from the less substituted carbon, it leaves from the more substituted carbon because that's where the positive charge is more stable. But there's a problem with that. Is this hypothesis consistent with our observations?
Where if we were SN1, would we get both stereochemistry?
Right. If it were SN1, you could attack from above or below, and so we would expect to see not just the Br trans to the OH, but also cis. But in fact, we don't. We only observe this diastereomer, and not the other one where the Br is on the same side as CH minus. So our observations are inconsistent with a carbocation intermediate, but they are also inconsistent with a purely SN2 mechanism where the nucleophiles got to get in really close before the leaving group leaves. So what is our solution to this conundrum? Our solution is that going from the protonated epoxide to the product is concerted, but the bond formations and breaking don't all happen at the same time. So briefly, a concerted reaction is one in which there's only one transition state. A concerted asynchronous reaction is one where there's only one transition state, but not all the bonds are the same percent formed or broken in the transition state. So you could imagine a transition state for this reaction in which I'm not sure how to do this. You can imagine a transition state for this reaction in which the OH has already begun to leave and is mostly gone. That would leave a buildup of partial positive charge on carbon A. But at the same time, the nucleophile had started to come in, but wasn't totally there yet. So you can imagine a transition state where the carbon-oxygen bond is mostly broken and the new carbon-bromine bond mostly not formed yet. But whatever percent broken this bond is, it's not far enough away that you have a full carbocation on carbon A. That OH group is still shielding the top face, And so the nucleophile comes in from the bottom. This is sort of an SN1-like SN2 transition state. What do we mean by that? Well, do you remember when we drew an energy diagram where on this axis we had nucleophile attacks, and on this axis we had leaving group, on this axis we had leaving group leaves, and we talked about how the SN2 pathway would go, all of that happening at the same time, whereas the SN1 pathway would go here, leaving group leaves, and then we make the product. What we're proposing for the epoxide is something like taking the transition state for this reaction and pulling it more towards the leaving group leaves without the nucleophile really changing how far it's come in. So here's our protonated epoxide reaction pathway. Still concerted, but there's way more positive charge on the alpha carbon than there is in a typical SN2 reaction. So you may not have appreciated that there's a continuum between SN2 and SN1. We'll explain that a little bit more because I think it's mostly unclear so far. I think I tried really hard and I'm not sure it went well. But the key point is you switch the regioselectivity for epoxide opening by changing the conditions. Strong nucleophiles attack the less substituted carbon because sterics. When you protonate the epoxide, the nucleophile comes in on the more substituted carbon because that's where the buildup of partial positive charge is more stable. All right, sorry about that. We're about a minute over. Have a great weekend.